Hello. In this video, we are going to talk about the instrumentation amplifier. An instrumentation amplifier is a type of differential amplifier which is typically used for precision applications, meaning to amplify a differential voltage signal in cases where the value of the differential voltage signal is very small, maybe in the range of microvolts, as well as when you're dealing with noisy environments, and it is noise that it is likely to be picked up on both inputs of your amplifier system, and so it can be considered common mode noise. It's present on both inputs. And in those cases, the instrumentation amplifier performs very well because it is typically a circuit with very high input impedance, very low noise, very low offsets, and very importantly, a very high CMRR, common mode rejection ratio. Now, we have studied the difference amplifier, which is also a circuit that amplifies a differential input signal, and it also rejects any common mode signals. However, there are several advantages that the instrumentation amplifier has over the difference amplifier, and we're going to see those in a little bit. But first, let's take a look at the analysis. Let's perform the analysis of the instrumentation amplifier to figure out an expression for its output voltage. Again, with the key characteristic of the instrumentation amplifier, I would say, is that it has a large CMRR. But if you look at a datasheet for an inamp, sometimes they're referred to as inamps, you'll see that it also has typically low input offset voltage, input bias currents, so low offset parameters. So it is a high precision type of circuit. So large CMRR, what I'm talking about, that is greater than 100 dBs typically. So typical value for an instrumentation amp could be 120 dBs. And again, it's good for precision applications. Let's go ahead and proceed with the analysis. As we can see, it is comprised of a differential amplifier. That's the second portion of the circuit. So this is just the standard difference amplifier with a gain of 1. And another 2 op-amps at the input that are configured as input buffers. So we could consider this the input buffer stage. Now, if we look at the circuit and we try to come up with an expression for the output voltage in terms of input voltages V1 and V2, we can start by labeling the current flowing through the Rx resistor. Notice all resistors are of equal value R except for this resistor R sub X. We're going to refer to it as the gain setting resistor, and we'll see in a second why. But if I label that current as Ix, then I can notice that the voltages on both sides of resistor Rx are equal to V1 and V2 respectively, because all those two amplifiers are configured as buffers, and so the voltage on both inputs of the amplifier should match, and therefore I should have a voltage value here equal to V2, voltage value here equal to V1. So I can write an expression for Ix as V1 minus V2 divided by Rx. Now that Ix current, since there is no current that can flow into the input terminal of an op-amp, all that Ix current must be flowing through both R resistors that are adjacent to Rx. And so the current flowing through this resistor is also Ix, as well as the current flowing through that resistor. And so I can label my voltage here VA, and then Ix times R. After an Ix times R volts drop, I get V1. After an Ix times Rx volt drop, I get V2. And after another Ix times R volt drop, I get another voltage here, VB. And so I can write my VA voltage as V1 plus Ix times R, meaning it's a voltage higher than V1 by a value Ix times R, which is the voltage drop across that bottom R resistor. And I can write VB as V2 minus Ix times R, meaning the voltage after a voltage drop through that Ix times R resistor. My output voltage is going to be the difference between VA and VB, because VA and VB, notice that they're being fed now into the input, into the two inputs of a difference amplifier stage of gain 1, because the ratio of the feedback and bottom resistors R to the two input resistors is equal to 1. And so I can write my output voltage as simply VA minus VB. Notice that the voltage that has the positive value, or the positive polarity, is the one that is being fed into the positive input terminal of the difference amplifier. The one with the negative polarity is the one that's being fed into the negative input terminal of that final difference amplifier stage. And I have just written expressions for VA and VB, so I can rewrite this as V1 plus IX times R minus V2 minus, and then minus and minus makes a plus, IX times R. And therefore I can write my V out as V1 minus V2 plus 2 IX times R. But notice that IX, I have already written an expression of it in terms of V1 and V2, so I can further rewrite this as V1 minus V2 plus 2 V1 minus V2 divided by Rx times R. Or in other words, V out is equal to 1 plus 2R over Rx V1 minus V2 by factoring out V1 minus V2. And this is the expression for the output voltage of the instrumentation amplifier. Sometimes it's a little bit different. All those resistors aren't always equal to each other. In most cases they are, but sometimes they're not. And in that case, you can typically look in the datasheet of the instrumentation amplifier for an expression for the output voltage. Now, both in the instrumentation amplifier as well as the difference amplifier we had previously seen, it is very important that the resistors be very well matched to achieve a high CMRR value. And the instrumentation amplifier achieves that because it's typically built in a monolithic piece of silicon. So it's all those op-amps are not just put together as discrete devices, but rather they're all built together in a single IC. And therefore it is easier to achieve good matching among resistors. There is typically one resistor that is left outside the chip to be connected externally, and that's resistor Rx. It's defined as the gain setting resistor, because the way you will set your gain, meaning the differential gain, the 1 plus 2R over Rx, that is basically the gain of that differential input signal, or applied to that differential input signal, is it's going to be determined externally by that Rx resistor. Is the one that you can program, so we say it has a programmable gain. Whereas the R resistor is just going to be a set of internal resistors whose value are just going to be depend on the manufacturing. Sometimes you can also find instrumentation amplifiers that have all the resistors be internal, and they just come with different values of gain, and so you can purchase it with a particular gain already. But if you wanted a programmable gain, this is the one that you are most likely to encounter. The advantages we said we were going to mention. Over the regular difference amplifier. Well, one of the disadvantages is obvious. It's going to use a lot more devices, so a lot more room, typically a little bit more expensive. The advantages is one, it has increased value of input resistance, because notice that the input signals are being fed now into buffer stages. Second advantage is that it has, I should say, larger R in, has a larger CMRR, in part because we have very good matching of resistors. And then I should say easily programmable gain. because you only need to change one resistor to set the gain, whereas in the difference amplifier, there were two resistors that you will need to configure to set the gain to a particular value. Let's take a look at a little example. If we wanted to, let's say, design an instrumentation amplifier to implement the following function: V out equals 100 times V1 minus V2. In that case, we could just say my equation 1 plus 2R over Rx is equal to 100, which means 2R over Rx is equal to 99. And therefore, my R is going to be equal to 99 Rx divided by 2. So I can pick a value for R. That will be 49.5 Rx. So I can pick my values. For example, let's say I choose my Rx equals to 10K. And in that case, my R will be 49.5 times that. So just to make it easier, then let's just pick 1K. And 49.5 kilo ohms. So that will be an example. Now, in all reality, most often the R will just be whatever it is, and you will only be able to select your Rx. Now, notice that in terms of circuit performance, or the most important performance parameter being CMRR, I can express my differential input signal, in this case, my VID, as V1 minus V2. And let's imagine that I had some common mode signal, which I'm going to represent as N for noise, because typically when you have an instrumentation amplifier, you're trying to get rid of any common mode signal, so that wouldn't be considered part of your signal, but rather part of your noise. Then I expect my my output voltage from the differential input signal. It's going to be my differential gain times VID, my VOCM, output voltage due to common mode signal, is going to be ACM times my common mode input noise N. And I can divide this first equation by the second equation, VOD over VOCM. Will be equal to AD over ACM times VID divided by VACM, or what we have referred to as the common mode noise. And so notice that this expression here will be equal to the CMRR, is the ratio of AD to ACM. And what we have on the left side of the equation is the output, the differential output signal divided by the common mode output signal, or the output signal due to the common mode, which we consider part of the noise. So this could be a measure of the signal to noise ratio at the output, SNR out or O, equals CMRR times, and VAD over the noise will be an expression for that times signal to noise ratio at the input. And so this is also an equation that's important to remember. Something that we haven't mentioned before, but that it's important to know, is that we keep referring to the CMRR. We mentioned the CMRR can be measured linearly as simply AD over ACM, or it can be measured in dBs, which is more often than not the case. The CMRR in dBs is also sometimes referred to as simply the CMR, the common mode rejection. And it will be 20 times the log base 10 of AD over ACM. And that's it. Typical applications for the instrumentation amplifier. We already mentioned them generally. More specifically, medical equipment, because you're dealing with very small signals and sometimes you pick up noise, 60 Hz noise from your equipment. So those will be cases where you can use an instrumentation amplifier. Automotive systems, control systems, and audio applications and any other high precision applications that you can come up with. So there's a wide range of areas where you will find instrumentation amplifiers. Again, normally you wouldn't find them built with discrete components, but rather a single IC in order to get the performance that you need out of them, a single IC that is already an instrumentation amplifier, and the internal build of it already contains several op amps. Thank you.